Welcome to our lesson about bend allowance. You may be wondering, what exactly is bend allowance if you've never worked with sheet metal before? Well, when a sheet is bent in a press brake, the part of the sheet close to and in contact with the punch elongates to compensate for the given bend. If you compare the length of this part in my example here, before and after the bending, you're going to find that they're different. As engineers, if we don't compensate for this variation, the final product won't have accurate dimensions. Of course, this is more critical for parts where you've got to maintain a tighter allowance or precision. If all the variables in my diagram are already making you zone out, fear not. This tutorial is by no means an exhaustive discussion about metal bending theory. However, I do cover some of the basic problems and principles you'll have to deal with regularly when working with sheet metal. Before we get rolling, I wanted to comment on something. There's not really a scientific method or formula for determining a truly exact calculation of the bend allowance, and that's because there's so many factors at play during the production of your sheet metal part. For example, actual material thickness, an infinite variety of tooling conditions, forming methods, on and on and on. There are many variables here, and in reality, many methods are used to calculate bend allowance. Trial and error is probably the most popular one. Bend tables are another popular method, and we'll be learning about those in this video. Bend tables are usually available from metal suppliers and manufacturers, as well as in engineering textbooks. Some companies develop their own bending tables based upon their own standard formulas. Let's get back to SolidWorks. How exactly does SolidWorks calculate bend allowance? SolidWorks actually uses two methods, bend allowance and bend deduction. I'm going to explain what these methods are and show you how they're used in SolidWorks. The bend allowance method is based on the formula that I've got up here in my diagram. The total length of the flattened sheet is equal to the sum of L1, that's the first length, and L2, plus the bend allowance. The bend allowance region is shown in green in my diagram. This is a region where, in theory, all deformation occurs during the bending process. Generally, the bend allowance is going to be different for each combination of material type, material thickness, bend radius, bend angle, and different machining processes, types, speeds, and so on. Truly, the list of potential variables is very extensive. The value of the bend allowance that comes from sheet metal suppliers and manufacturers, as well as engineering textbooks, is provided in bend tables, and a bend table looks pretty much like what I've got on my screen now. This is an Excel spreadsheet. The bend table approach is probably the most accurate approach for calculating bend allowance. You can input your data manually into a matrix of the bend angle and bend radius. If you're not sure of the bend allowance value, you can run some tests. You need a piece of the exact same sheet metal you're using to manufacture your part, and then you'd bend it using the exact processes that you'll be using during your machining. Just take some measurements before and after the bending, and then based on this information, you can adjust the bend allowance as needed. Another method that SolidWorks uses is the bend deduction method. The formula is as follows. The flattened length of the part, that's LF, equals D1 plus D2 minus the bend deduction. There's D1 and there's D2 minus the bend deduction. As with bend allowance, bend deduction comes from the same sources, tables and manual testing. As you can see, it's easy to imagine how these values are related to each other based on what these formulas indicate. Another method for calculating bend allowance uses the KFactor, where K is the neutral axis offset. The general principle of this formula goes like this. The neutral axes are in my diagram here in red. They don't change during the bending process. During the bending process, the material inside the neutral axis will compress, and the material outside the neutral axis will stretch. The neutral axis will be closer to the inside bend. The inside bend is indicated in blue in my diagram. The more the part bends, Now, the more the part bends, the closer the neutral axis will lie to the inside of the part. The K-factor, as we've seen here, equals T, or the offset distance to the neutral axis. We divide that by big T. That's the thickness of the material. In this formula here, the bend allowance equals 2 times pi multiplied by A, that's the angle, multiplied by the sum of R, the bend radius, plus the K-factor, multiplied by T, the thickness of the material. And then you divide all of this by 360. In theory, the K-factor can be anywhere between 0 and 1, but for practical purposes, it's more like 0.25 to 0.5. For example, you'll find that hard materials like steel have got a higher K-factor, such as 0.5. Softer materials like copper or brass are going to have a lower K-factor, closer to 0.25. And don't worry, that's the last formula we'll be walking through in this lesson. It might seem a little bit confusing now, but once you practice it a little bit, it'll become second nature. One last point here. Let me take a look at an example. There's a wiped hem on this part. It's got a K-factor of something like 0.3. On the other hand, a softer bend, or for example, the gradual bend that I've got on the other side of this part, has got a higher K-factor of about 0.5. And this concludes our lesson on bend allowance.